So we've seen how to use Kalman filters of different types to perform state estimation given known parameters and parameter estimation given known states independently from each other. We'd really like to be able to do both at the same time. We'd like to be able to estimate both the states and the parameters of our cell model using noisy measurements. And there are two Kalman filter-based approaches to doing so. One is called joint estimation and the other is called dual estimation. And we're going to discuss those in this topic area in the next subsections. The generic idea to joint estimation says, well, previously we've thought of the state comprising the quickly varying things and the parameters comprising the slowly varying things. But let's be honest with each other, they're both varying, so why don't we just combine them all together and call the whole thing the state of the system? So jointly, we are putting together the thing that we used to call x and the thing we used to call theta, and we're calling that our new x, maybe a big X or something like that. And we come up with equations that jointly describe the variation of the state and the parameters, and we just employ a standard SPKF or EKF on the large augmented state. So there are advantages and disadvantages to this idea compared to what we're going to call dual estimation in a little bit. This has first large matrix operations because remember that the covariance matrix is going to be as tall as x plus theta and as wide as x and theta. So I get this large matrix with lots of values in it. And if I don't expect the variation in the state to be too correlated with the variation in the parameters, I would expect values close to zero here and maybe not close to zero in other places, which means that when I multiply by these matrices and so forth, I'm doing a lot of multiply by zeros, which isn't very efficient. So there's large matrix operations compared to what we've done before. Also, we have hugely different timescales on the states of the augmented vector, so the old states and the old parameters, what we called states and parameters before. The states would change quickly, the parameters change slowly, which means that the fictitious driving noise, remember I'm going to have a sigma W driving the states and a sigma R driving the parameter dynamics, and sigma R is going to be much smaller than sigma W because the parameters change so slowly. So inside these covariance matrices that I get as a result, I'm going to have tiny values and big values, and if I work with infinite precision math, that's not a problem, but I don't. I use finite floating point math, and usually not even doubles, usually single precision in some implementation. Sometimes people even do fixed point, which probably is going to be really hard to do here. But suppose we just have simple floating point math, and I add together a big number and a small number. Well, the effect of adding a small number completely disappears because I don't have enough decimal places basically to store the difference, and so we get round-off error and some numeric conditioning problems that may lead to matrices becoming non-invertible and non-symmetric and so forth, and that will cause problems. So we have to be concerned about that and to think about that when we are determining between joint estimation and dual estimation. The biggest benefit, well, actually there's two benefits of using joint estimation. One is that it can be more accurate because you are considering the interactions between the state and the parameters and how much an uncertainty in a parameter results in an uncertainty of a state and so forth. So you do tend to get a little bit more accurate results using joint estimation than what we're going to call dual estimation. The other one is that it's very straightforward to think about how to implement it. What we do as already suggested, we take the state and the parameters and we put them in one new state vector, and we have the equations describing how they work, and we stack those together too. So the state equation works as it did before, and the parameter equation works as it did before, but they are now joined together vector-wise, whereas before we were thinking about them separately. We're going to call this whole thing fancy xk, and we're going to call that whole thing fancy f for the function implemented by the dynamic function implemented by the system. And we're going to combine the randomness of r and w, and we're going to call that fancy w. And so together we have a dynamic that looks like this here, where I've got big state equals new fancy function times previous big state, previous input, and previous combined noise sources. And then the measured output, assuming that I'm measuring voltage in both cases, which I probably am, is simply the voltage equation with the big state and the input and the sensor noise. So I think about this exactly the same way I would think about a normal EKF or SPKF. I just have this would be different, and I would combine noises together in that, and my X would somehow combine the parameters and the states together. The dual estimation problem is a somewhat different idea. And this is saying, well, I know that states move quickly and parameters move slowly. I'm going to use two different Kalman filters. One estimates the states and the other one estimates the parameters. And I will share variables or signals between these filters so that both can do their job. And the computational complexity is smaller because we have smaller matrices involved in the matrix operations. And because I'm not combining in the same filter the slow time constants and the fast time constants, the matrix operations may be numerically better conditioned. So those are the advantages. A disadvantage is you are decoupling the state from the parameters, so any cross correlations are lost, and so we may have somewhat poorer accuracy. And I think it's also a little bit more conceptually challenging to think about the dual estimation than the joint estimation. So what we do when we're considering the state of the system, we have a filter that estimates the state, and we use these dynamics that we've seen before, and we're explicitly including the parameters in our state equation. And again, any time-varying numeric values required by the model are embedded in here, and any non-time varying values are simply constants inside of f that we don't estimate. And we revise our model of the parameter dynamics, and there it is. But we're going to include in the output equation, first the output equation is going to be the same H, so voltage in both cases, but I'm going to include the equation that describes X. So this is X, and the equation that describes X is this one. And that gets included right in there explicitly. I'm going to need to remember that carefully a little bit later on. But everything else is the same. I've got the U, V, and theta, and possibly I replace V with E, or possibly I use the same thing. I have a picture here that draws the signal flows between the two different filters. The interactions I summarize in a table in an appendix to this chapter. We don't really talk about it in more detail here, or a lot more detail anyway. But you can see on the top the blue blocks are corresponding to a state filter, kf sub x, to estimate the state. So the time update is steps 1 ABC, the measurement update are steps 2 ABC. And then on the bottom we have the green colored blocks for the theta Kalman filter with steps 1 ABC in the left one and steps 2 ABC in the right one. And the signals required by each filter and each operation can be determined by going through the equations and seeing which parts of which steps require which signals. And it turns out I can do this in a causal way if I'm careful. The first thing I believe we do is we compute our theta prediction, which goes into predicting x as well. And so we predict x, which would be this middle signal here. And we also predict theta going in here. In our measurement update, we use the previous value of x here and so forth. You can follow all the signals through. So there's coupling between both filters, and we estimate overall the output is going to be the estimate of the state, the estimate of the parameters, and if you want to also for error bounds, you can have here would be the covariance sigma x tilde k plus, and here I would have sigma theta tilde k plus coming out. It's called k minus 1 over here because in the feedback it gets delayed by one sample before I use it the next time around. So I'm essentially running two Kalman filters, nonlinear Kalman filters, in parallel, one adapting the state, one adapting the parameters, and there's some information exchange between the two filters. Those are the generic ideas of joint and dual filtering. I'm going to briefly comment on some application notes of applying EKF and SPKF in particular to these two different methods. So first we look at joint state and parameter estimation using EKF, and this is straightforward. Remember what we are doing is we are gluing the state and the parameter together in an augmented state, and that's the same thing as going back to the previous chapter, looking how to do a nonlinear EKF for state estimation for this augmented state. But when we're doing the derivatives for C hat and D hat and A hat and B hat, don't forget the recursive calculations that we need to do. That's super important. I guess that's for A hat and B hat. Dual state and parameter estimation, running two different EKFs, is fairly straightforward, except we must always remember when we're computing the C hat and the D hat matrices that we have to use total differential equations. We can't use just simple partial differential equations to implement their results. So we have to do all of the math, make sure that we're doing it right. So C hat is the total derivative of the g function with respect to theta, and we go through the steps and find that dg by d theta is partial g with respect to theta plus partial g with respect to x times dx with respect to theta, and that's dx minus, and dx minus with respect to theta is written in terms of the previous dx plus with respect to theta, and the previous dx plus with respect to theta is written in terms of the previous dg by d theta. So this is kind of a tricky chain of events. I need this and this. So these are prior versions of each other. And then this and this are, one is a prior version, and then that is there as well. And then finally this and this, one is a prior version. So what do? You initialize this to something at the beginning of time, you initialize that to something at the beginning of time. That allows you to compute this, which gets plugged into this equation, which gives you this, which is plugged into this equation, which gives you this. So next time around, I have that available, and I have that available, and that allows me to compute the next steps. So it's completely doable, but you have to be very careful to follow the math through, otherwise it just doesn't work. Now, if you do your derivation yourself, you'll say, wait a minute, this L, the Kalman gain, is equal to some covariance matrix operations, and some of those covariance matrix operations are a function of theta, and here we have basically assumed that is not true. So we have assumed that the variation in the Kalman gain as a function of variation in theta is so small that we don't bother worrying about it. There are papers where people talk about that, and they run the filters both ways with variation in this too, which is much harder to do, and the results that I've seen seem to indicate that it's really not worthwhile doing extra computation. So again, in this case, there's 3 total derivatives that we need to update. They're computed recursively. We initialize to 0. That's using EKF. Using SPKF for joint estimation, there's no drama. We use the standard SPKF steps with the augmented state vector, and that just works. The dual state and parameter estimation, there's no drama. We just use 2 filters, and we intermix signals. And there are tables in the back of this chapter of notes, summary tables of the algorithms that show you exactly what steps are taken in what order to implement these filters.